What's going on, math people? We're back, and this time we're talking about related rates. Now, key word in this is the title, related rates. When we're thinking about rates, we're thinking about calculus-wise the first derivative. All right. When we're thinking about related, it's talking about how different rates are related to each other, or affect each other. All right. So let's jump straight into the game plan. With related rates, you have to read carefully. Point blank period. And you have to identify what you want to find, draw a picture when possible, extract pertinent data, and differentiate. And every time this differentiation will be implicit differentiation. All right? Because every differentiation is going to be with respect to time because we're talking about rates. All right, so let's jump straight into this example. All right, on a morning of a day when the sun will pass directly overhead, the shadow of an 84-foot building on level ground is 35 feet long. At the moment in question, the angle theta the sun makes with the ground is increasing at the rate of 0.26 degrees per minute. At what rate is the shadow decreasing? Remember to use radians in your calculations. Express your answer in inches per minute. All right, so here we go. We got all these little issues, right? First of all, we have this little. Look at this this mess at the end. It says, remember radians, but it gives us all this stuff in degrees, so we have to convert degrees to radian. So we're going to take the given degree times power of 180 to get that conversion. And it also says make sure your answer is in inches per minute. But it gave us the doggone problem with everything in feet. But it's okay. We know that there are 12 inches per 1 foot. All right, so we have, that is careful reading, catching those little intricate details right there. Now, it says on the morning of a day when the sun will pass directly overhead, the shadow of a building right there is, the building's 84 feet tall. So I'm just going to go ahead and draw me a little picture that reflects the little. All right, so this thick blue portion right here, that'll be my building. All right, my building is 84 feet. Oh, my building is 84 feet tall. All right, 84 feet tall. Then up here, I had the sunshine. Let not all of its beauty. Yeah. All right, I got my sunshine right there. And it casts a light. And then the shadow at the bottom. The building shadow is in red. All right. All right, so the sun is making an angle right there. All right, I drew a quick little picture. All right, this will be my y-axis. This will be my x-axis, just for reference. All right, so looking back at the problem, let's see what other pertinent information I have. It gave me a rate in the problem. The rate that it gave me, it says d theta dt. It said it was rate in degrees, 0.26 degrees per minute. All right, so we need to convert that degrees to radian. So let's go ahead and we'll take that 0.26 times pi over 180 and that's going to give us, let's go ahead and run that through the calculator right quick. 0.26 times pi divided by 180. We're going to say 0.00454. 0.00454 radian per minute. All right. And what else does the problem provide us with? All right, so we've drawn our picture. We're extracting data now. And it says that the shadow in the moment is 35 feet long. So I'm going to go ahead and put down here 35 feet. All right, and it wants us to find at what rate is the shadow decreasing. All right, so remember that the shadow is represented by the x-axis, so the problem is telling us to find dx dt. All right, so let's see. We have an angle present. We have, anytime you see an angle present, the majority of the time that you see an angle present in your problem, you're going to use some form of a trig. And so we have x-axis values, y-axis values. We can quickly say, use tangent. Tan theta is equal to y over x. Notice that y is the building height, and that's static. It's not going to change. So we can look at that y as a constant. So when we take the derivative of using implicit differentiation with respect to time, we'll have derivative of tangent is secant squared theta d theta dt, because we're differentiating everything with respect to time. And if we were to rewrite this, taking y as a constant, this would be the same thing as y to the negative 1. And so we would have negative y times x minus x squared dx dt. So we have secant squared theta d theta dt equals negative y over x squared dx dt. And I'm just going to run over this guy real quick. Run over this real quick because I want you to pay it close attention that dx dt is what we're focusing on. We're focusing on finding dx dt. All right, so we have before us more information that we need to calculate, because when we took the derivative, we introduced another function, the secant. And we know that secant theta is r over x whenever we're talking about the size of a triangle. And this is definitely a right triangle. And so we can use we'll use the Pythagorean Theorem to find out what the hypotenuse is, the r, and we have 35 squared plus 84 squared equals r squared. And when we run this through our little handy dandy calculator, 35 squared plus 84 squared, we get 8281. 8281 is equal to r squared, and 91 is equal to r. So now we could do some quick substitution. Instead of saying secant squared theta, we can write out what secant is, and that would be 91 over the x value of 35 squared and d theta dt. As a matter of fact, we can go ahead and start plugging in all of our information. D theta dt is 0.00454 radian per minute, equal y is negative 84, x is 35, and we're trying to find dx dt. All right, so, and that's supposed to be 35 squared. Forgive me there. And whenever we go ahead and start solving for dx dt, we will multiply each side by 35 squared. After simplification, we have 91 squared times 0.00454, and I did a no-no by not putting the unit on that. And divided by negative 84 feet, and this is 91 feet up here. Units are important. All right. Equals dx dt. All right. Now we will toss this into the calculator. We have 91 feet, 91 squared times 0.00454 divided by 84. It wasn't squared. It was just 91 times 0.00454. Let me make sure I'm not tripping. It is squared. All right. And that will give us 0.447, we'll say 0.4476. 0.4476 feet per minute is equal to dx dt. Have we satisfied this problem? No, we haven't, because the intricate detail that was up here said make sure it's in inches per minute. So we need to convert that feet to inches. So in order to do so, we will multiply this guy by 12. Multiplied by 12. 12 times 0.4476 and that gives us 5.3712, 5.3712 inches per minute. Notice that those details are very, very important. And we have calculated dx dt. All right. Related rates problems is really focused on getting into the details and make sure you're paying attention. All right. Remember that related rates problems will always use some form of implicit differentiation because you're going to be differentiating everything with respect to time. With that being said,